Today we will learn with this idea of how an object accelerates when a net force acts on it. Are you familiar with the formula of acceleration, which is equal to change in velocity divided by the time interval? This definition implies on how the cause of acceleration is force. A further explanation of that would be how unbalanced forces acting on an object cause the object to accelerate. An example would be when a hockey puck is at rest, the net force on it is balanced, so the puck is in equilibrium. Hit the puck and the puck experiences a change in motion. It accelerates. Apply another force by striking the puck again, and the puck's motion changes again. The combination of forces acting on an object is the net force. Acceleration depends on the net force. To increase the acceleration of an object, we must increase the net force acting on it. An object's acceleration is directly proportional to the net force acting on it. Acceleration is directly proportional to net force. It can be kicking a football that neither remains at rest nor moves in a straight line. So now that we know how force causes acceleration, what causes an object to accelerate? For a constant force, an increase in the mass will result in a decrease in the acceleration.
An illustration of how mass resists acceleration would be when you push on an empty shopping cart, then push equally on a heavily loaded shopping cart. The loaded shopping cart will accelerate much less than the empty shopping cart. Acceleration depends on the mass being pushed. The same force is applied twice as much as the mass results only half the acceleration. The acceleration is inversely proportional to the mass. Acceleration is dependent on the mass that is being pushed. But how does the increase in mass affect acceleration? Now, we know that Newton's first law explains what happens to an object when there is no force acted on it. It either remains at rest or moves in a straight line with constant speed. So, what happens to an object when the force is not equals to zero? Newton's second law answers this question.
Newton's second law states that the acceleration produced by a net force on an object is directly proportional to the magnitude of the net force, is in the same direction as the net force, and is inversely proportional to the mass of the object. The acceleration of an object depends on its mass as well as the force exerted on it. Newton's second law also can be used to calculate the net force if mass and acceleration are known. To do this, the equation for Newton's second law must be solved for the net force F. Newton's second law describes the relationship among an object mass, an object's acceleration, and the net force on an object. By using consistent units such as newtons for force, kilograms for mass, and meters per second squared for acceleration, we get the exact equation if A is acceleration, F is net force, and M is mass.
It is directly proportional when the acceleration is equal to the net force divided by the mass. If the net force acting on an object doubles, its acceleration is doubled. It is inversely proportional if the mass is doubled, then the acceleration will be halved. If both net force and mass are doubled, then the acceleration will be unchanged. Now, what is the relationship among an object's mass, an object's acceleration, and the net force of an object? Newton's second law states that the net force acting on a body is proportional to the body's acceleration. This implies that when the sum of all forces acting on the body increases, the acceleration of the body also increases. The direction of the body's acceleration is in the same direction as the resultant force acting on it.
To determine the graphical analysis of the relationship between the force and the acceleration of an object with a constant mass, we will now be conducting experiment 3, all about force and acceleration. For this experiment, the following materials we needed are linear air track, sets of masses, and millisecond timer. We will now be doing following step-by-step procedure when performing the experiment.
First, we position and level the air trap. Second, we weigh the glider along the OK strips and place 40 grams mass on it, which is 20 grams on each side. Third step, we tie a string to the glider and let this string pass over the pulley located on the other end of the air trap. Then, tie the other end of the string to the weight hanger. Fourth step, to determine the relative position of the photo eye detector, the relative position of the photo eye detector can be read from the distance scale attached to the air trap.
Fifth, set the timer range switch to a range that displays 4 significant figures, and the function switch to A start, B stop. Connect the cable from the magnetic starter to timer input A, and the cable from the photo eye to timer input B.
Sixth step, hang the 20-gram mass on the weight hanger. Seventh step, release the hold button. Record the time for the glider, starting from rest to move the distance. Make 4 time measurements. Eighth step, repeat the following steps 6 and 7 and hang the masses at 20 grams interval. Do this until the total mass on the weight hanger is 100 grams. Last and final step, plot the graph of the force which is given by weight of the hanging masses plus the weight hanger versus acceleration and determine the slope of the graph.